Can we be okay with it being a sheet that's just kind of 3D, but not very good 3D, like mediocre 3D, like Mr. Shelton D? It's just okay, okay? And again, I want to recognize there's an above portion and a below portion here, but we're going to say the sheet is infinite in all directions because we're trying to do the infinite sheet. But I need to impress upon you, as I keep saying, infinity isn't as big as you think. So it's just big compared to your size away from it. So we're going to talk about the fact that we're going to be very close to the surface of the sheet. And that's what makes it an infinite sheet. There's an electric field, and we talked about why we believe that the electric field kind of has a collimated look to it. And what I mean ultimately is that the electric field streams away from the sheet in two directions, above the sheet and below the sheet. Is that good? We get an idea about this? So when we're trying to use Gauss's law, step one is really about using your imagination and ask yourself, what do you think the field looks like? You're trying to imagine the field lines because we need to have an idea about what the field must be like before we use Gauss's law. Because we're going to be choosing a Gaussian surface, and we want our Gaussian surface to do its best to exploit the symmetry of the system. If there's no exploitable symmetry, Gauss's law is the wrong choice. I'm going to say that again because this is a deal breaker. After we get we do the first step and we're going to the second step, you're really choosing whether Gauss's law can solve this problem for you or whether you'll have to use something else. And we only have two choices when it comes to trying to find the structure of the electric field. We can use Coulomb's law, which adds up all of the contributions to an electric field, or we can use Gauss's law, which attempts to exploit the symmetry to make the electric field something that is a constant everywhere along your surface. So this is where you should ask yourself, is Gauss's law a good fit? Is there exploitable symmetry? Now, if there is, go along with Gauss's law. If there isn't, you're going to do something else. So I think there's exploitable symmetry here, which brings us to the next step. Choose your Gaussian surface carefully. There are parameters for a Gaussian surface because Gauss's law requires that your surface be completely closed and bounded. That's the first thing. It must be an enclosed surface with no holes in it. Second, you're probably going to want to place it symmetrically around your object. So that's what we're going to try and do here. We're going to try and place it symmetrically about our object. So I'm going to start by thinking that, what surface would I use? And I chose a cylinder when we talked about this last week. And I chose a cylinder that cut through the surface and was half above the surface and half below the surface. Something like that. And I tried to make it equal distance both above and below the surface. And I tried to, make sure that it was arranged so that my cylinder was perpendicular to the surface itself, cutting through it in such a way that the electric field lines would only be piercing the top and bottom of the cylinder, and that there'd be no electric field lines piercing the sides of the cylinder. So that was the choice I made. And I gave myself parameters for this cylinder. One of the parameters was to make the cylinder have a height of 2h, so that there's an h above and an h below the surface. So my total height of my cylinder was 2h. I also gave the cylinder a radius of r, making the area of my top pi r squared. Now, those are the parameters for my surface. Now, there was other parameters that were given to us in the problem. Something like maybe the charge of the sheet was Q, and the surface area of the sheet was A. That's not an unreasonable thought. Or we could use, and what we will use, is the charge density of the sheet is sigma. You'll need to make a choice here based on what you're given. In the future, our charge sheets are going to have a finite charge on them because we're going to use them in predicting the storage capacity of a capacitor. And they'll have a finite charge. We'll say Q over A. But there's also the possibility you'll be asked for the charge density of a surface. And you can use Gauss's law to figure out charge density for a number of ways. We're going to see one today. So keep in mind that either of these is fine. And it doesn't matter which one of these you're given or which one of these you use. You need to be flexible. Now, the actual calculation of Gauss's law, or the use of Gauss's law, is separate from this. Once you have established all these things, applying Gauss's law is its own set of things to do. So once we've chosen our Gaussian surface and made some decisions about its size and shape, Gauss's law has two parts. There's the Q enclosed side, and then there's its proportionality to calculating flux. Now, once we have that understanding that that's what it is, we can choose to work either side. We focused on doing the flux part first, and then we tend to rush through the Q enclosed. So this time, let's do the Q enclosed size first. That way, we can rush through the flux part later. Q enclosed has to be the amount of charge that you have trapped inside your surface. We have trapped a disk of charge inside our surface. That disk of charge is right here. This is the disk of charge that we have trapped inside the surface. And that disk of charge has the same area as the top and bottom of the cylinder. Now, by the way, is there anybody in here who realizes we didn't have to use a cylinder? We could use a square or a rectangle or even a prism would have worked just fine as long as we erected it right. So there's no reason why a cylinder was the only choice. You could have chosen anything where the sides were perpendicular to the sheet and the top and bottom had the same area. So there was no reason we had to choose a disk. But the area of our disk is going to be pi r squared. This is the area of our surface enclosed. So the charge enclosed will be this area times sigma. Or if you'd like, if you were given it in terms of charge and area, you could do it this way too. One or the other, depending on what you were given in your problem. We're going to go with the version that has sigma in it. Now that's our charge enclosed. So over here, I'm just going to say we have Q, not Q. I have pi r squared times sigma. That's our Q enclosed. Now, epsilon times the flux, but let's go ahead and get the flux. I'm going to put something in here, but I think we can work the flux portion out. Our flux has to equal the sum over a closed and bounded surface of the electric field times the area, taking into account the direction between the electric field and the area. I'm going to take our surface and break it down into 3 separate parts: the top, the bottom, and the sides. So now, I'm writing it out a lot more than I'd probably expect you guys to do on your test. But doing this, if you're asked to derive, I think writing these things out just like this is a good call. Make sure your test graders know that you have to take into account all of the area of your surface. That means taking into account the entire structure and making sure you accommodate all of it. And carefully tell them that you understand this is the one that's going to 0. And we know that one's going to 0 specifically because there's no electric field piercing the sides of the can. It's the dot product that really is at issue here. The dot product is 0 because the electric field is traveling along the side of our surface, and our area is perpendicular to that surface. It's perpendicular to that direction. So that is a cosine of 90 degrees. There is electric field there. It's not an unknown. In fact, the electric field is probably some value all along here. So it's not that the electric field is 0, and it's not that the area is 0. It's just that there's no electric field going through the side of the can. Right? That's why we're zeroing this out. Now, the top and bottom, we can deal with the top and bottom. That part's not a problem. I think it's not unreasonable for us to take a look at each piece one at a time: the size of the electric field, the size of the area, and the direction between them. So let's handle the direction first. I always think handling the direction is the best way to go. So let's handle the direction first. I think we can all agree the electric field is coming from the surface, and it's piercing the top of the can, say here. And the area of the top is definitely in the same direction as the electric field. The bottom's going to have a similar issue, right? The electric field's going to be going this way. Electric field is going to be going this way, piercing the can, say here. And the direction of the area here is going to be away from the inside. So again, 0 degrees, both on the top and on the bottom. Do we see why that's true? Yeah. It's important that we make sure we get the direction correct, that it's not 180 degrees or something like that. I want to make sure you understand that we have electric field, we have a positive flux on the top of the can and a positive flux on the bottom of the can. Because the direction of flux is a comparison of the direction of the electric field and the direction of the area. You can have negative flux if the area is pointed one way and the electric field is going the other direction. So in this case, we have positive contributions to flux both on the top and the bottom. So when I come to look at these right here, immediately I can say for the top, it's going to be cosine of 0 degrees. For the bottom, cosine of 0 degrees. Next, I need to consider the strength of the electric field and the area, but I'm no longer dealing with direction. I've pulled my vectors off the top. It's kind of a sign to me that I'm no longer dealing with the direction anymore. I've handled that. Now my next question is, can I pull the electric field outside of the integral? Is there any reason to suspect that the electric field will be a constant along that surface? So I'm looking back at that, trying to decide, is the electric field a constant over the surface? And I think there's every justification to believe it is. The best justification is I am I am the same distance away from the sheet everywhere along this surface. Right? I'm a distance h away from the sheet. And I'm also a distance h away from the sheet for this surface. So I think the electric field is the same value. And moreover, I think the electric field here is the same as the electric field here because I chose to make sure my surface was right in the middle, right, with half of it above and half of it below. I didn't make that clear before, but I think the electric field is the same strength in both of these locations because I am the same distance away. So I come back to this. I'm going to rewrite it again. But this time I'm going to pull the E out. And again, I'm making it clear, I think these two E's are the same. So now I'm left with what I've been hoping to get every time I've done this. Go ahead.
When you say the same distance away, like, the same distance away from what?
From the sheet. So the sheet is here in the middle, and the bottom of the can is a distance h away from the sheet, and the top of the can is a distance h away from the sheet. Is that good?
Yes.
So we want to be left with something where we don't have to integrate if we can avoid it. We don't have to integrate this. This just says add up all of the area for the top. And the other one says add up all the area for the bottom. I don't have to do anything fancy here. The top is a disk. Its area is pi r squared. There's nothing related to the area that I have to take into account. I don't have to add up like something that's changing about the area or anything related to where I am in the area. I just need to add up the whole area and get an expression for the area. So for each of these, since the top and bottom have the same area, it's pi r squared and pi r squared, giving me a total electric flux that equals E pi r squared times 2. Right, 2 contributions. So again, we are trying to avoid having to actually integrate. We are purposely trying to set up the conditions where we're going to get some of the area, and we chose the shape, so we should know what the area is. By the way, if this was just a square, that would have just been s squared for the side length squared. I probably could have just said A for area. But I'm trying to make sure I'm utilizing geometry so that we feel as though we're looking at the geometry of a problem. All right, so that brings us back to here, where I can write 2E pi r squared. Now, again, our goal is to try and find the electric field. That's what we're doing this for. And so we chose a Gaussian surface. We split the Gaussian surface up into separate pieces. We evaluated the dot product for each piece first. We then attempted or tried to ensure that it was reasonable that the electric field was a constant during each piece. Pull the electric field out and then sum the area. That's what we tried to do. What we're left with is an expression we can solve for the electric field. So I'm going to cancel out the things that are the same on both sides. And I'm going to solve this for electric field, which is going to give me sigma over 2 epsilon naught. This is a constant. meaning the electric field near a sheet is constant, uniform electric field. This is important. If you want to build a uniform electric field, this is how you do so. There's a lot of reasons why you might want to have a constant, uniform electric field. All sorts of them. I'm going to explain one in just a minute. Everybody see how we got here, though? All right. I'm going to do something real quick that I think is worthy for you to have someplace. All right. Can't fill all of it in, but these are our major shapes. So for things in the next couple of weeks, we're going to deal with these shapes a lot. I'm highly, highly encouraging you to commit these to memory, especially the last one. It comes up so frequently, it's really worth knowing. But these are our basic shapes, and they have there's some clear, I don't know how you want to describe this. There's a clear trend here that it attenuates the most if you're dealing with a point charge, and it's constant if you're dealing with the sheet. So there might be reasons why you take that point charge and spread it out into a sheet if you're trying to get something uniform. That's how you would do it. But we've done it ultimately. If you can prove these using Gauss's law and showing all your work, then you'll have a firm understanding of how Gauss' law is supposed to work.